Hello everyone. In this presentation, we are going to understand how to prototype an electronic bike or electric bike by using some proof of concept using VA Microsystems LPC2148 development kit. Say for example, this blue color potentiometer is considered as a accelerator in our hand. Say for example, if I rotate it in this clockwise direction, I am saying that I am accelerating. If I am rotating in the anti-clockwise direction, I am decelerating. So when I want to accelerate means I have to rotate it in anti-clockwise direction. When I want to decelerate means I have to rotate it in anti-clockwise direction. So this is something like an accelerator pedal or accelerator knob in a two-wheeler or accelerator pedal in the four-wheeler kind of things. So when I accelerate, vehicle has to accelerate. When I rotate in clockwise direction means vehicle has to accelerate. When I rotate in anti-clockwise direction means vehicle has to decelerate. That is one thing I am expecting. And how the vehicle acceleration is being done? Through PWM. Yes or no? So PWM means is increasing the speed of the motor, or PWM is increasing the intensity of the light, or PWM varies the intensity of the volume. So PWM varies the volume, PWM varies the speed, or PWM varies the intensity. In our understanding, we are connecting the LED here to mimic the speed of the bike. So when I am rotating it in clockwise direction, I am accelerating. So the width of the pulse is increasing. So the brightness is also increasing, which is assuming that vehicle travels in a high speed. So for example, more the brightness. So if you see, I am rotating in clockwise direction, brightness increases. I am rotating in anti-clockwise direction, brightness decreases. So clockwise direction, I am accelerating, so brightness increases, vehicle is moving in high speed. Rotating in anti-clockwise direction, I am decelerating, so brightness decreases, so vehicle stops. So the input is analog through the potentiometer. The output is also analog through the pulse width modulation. So what do you understand from this? So there is this potentiometer is connected to ADC pin of your LPC2148 microcontroller. So the potentiometer output is analog, which is given to the ADC of LPC on-chip ADC of LPC2148 microcontroller, which converts it into 12-bit digital value. So this converted 12-bit digital value is sent out through I2C protocol to this 7-segment display. We know how I2C protocol based 7-segment display in VA Microsystem works. By using that principle, we are sending out the 10-bit analog to digital converted value, or digital equivalent of analog input in 10-bit is getting displayed in the 6 or 4 7-segment displays as we see here. Because it is 10-bit, the minimum value is 0. That is why the 7-segment display shows 0. And when I rotate it in clockwise direction, the voltage increases, so the output is also increasing. At the right extreme, the analog input is 3.3 volts. So the maximum digital output in 10-bit is 1023. So analog input is also maximum. The digital output is 1023, which is 10 bits maximum, and the brightness is also maximum. So this brightness is considered as a motor speed, and the potentiometer is considered as an accelerator pedal. This 1023 can be used as a dashboard. Dashboard shows it is traveling in high speed. When I am rotating in anti-clockwise direction, it becomes 0. At one end, it becomes 0. The other end, it becomes 1023. So in between, we are getting the intermediate values. See how fast the I2C protocol works inside the LPC2148 microcontroller, that we need to appreciate. So gradually I am rotating in clockwise direction. So the analog to digital converted value has become 100 now. Then analog to digital converted value become 200 now. Then 300. Then 400. Then 500. 600. 700. 800. 900. Then 1024. So the infinite values in analog is converted to 1024 finite values in digital, that is getting displayed in the 7-segment display. This analog to digital converted value given as a duty cycle value for the PWM. So whenever the analog to digital converter value is 0, duty cycle is also, so brightness is 0. Whenever the analog to digital converter value is maximum, duty cycle value is 1023, so it glows. The period is also kept as close to 1023, so it glows with full brightness. So varying the potentiometer varies the analog voltage. Varying the analog voltage where is the analog to digital converted voltage. This analog to digital converted voltage is given as an input to the PWM as a duty cycle value. So minimum the ADC value, minimum the duty cycle, minimum the speed, that means minimum the intensity here, maximum the duty cycle value, maximum the speed. This is how it works. So here this value, what is coming out from the ADC, is transmitted through UART to the PC, which you can say something like IoT, connected to connected cars or something like this. The speedometer value or the voltage value of this potentiometer is displayed in the PC. Okay, so through the Poderosa, here you can see, here you can able to see the voltage value. The voltage output of this kit is shown as 2046 millivolt or something. You are able to see that. Okay, so now we are reducing the value to 0. Let me check the voltage output is 0. It is better to view through magnifier for more convenience. Yes, there is a magnifier. I am increasing the magnifying the values, right? Going up, now we can able to see up to some extent, right? So now we can see. Okay, let me magnify much more. Yes, yes. Now you can see magnifier. Now you can see the potentiometer value, gradually I am increasing, brightness is also increasing, and the value in the screen is also increasing. So maximum value 1023, maximum brightness into 2, 1023 into 2, 2046. Minimum value 0, unlike to digital control, output is 0, potentiometer value is 0, brightness of the LED is also 0. So in between, so now it is 250, here it is 500. So the analog to digital converted value is multiplied by 2 and then transmitted through UART to PC. So now the concluding statement here is the on-chip peripherals and off-chip peripherals are on-chip peripherals and off-board peripherals inside this microcontroller as well as the development kit helps us to make a proof of concept of several applications here. So for example, how many on-chip peripherals are being used? Let us see. Here when I rotate in clockwise direction, you can see the LEDs are just blinking. So the ADC output is directly given to the GPIO. The ADC output is directly given to the GPIO. So where I gradually increasing means, so the 10 bit, because 10 bit ADC is 10 bit ADC output is coming out in the display. Say for example it is 10. So converted value here it shows is 10. 10 means what? It's a decimal, its binary equivalent is 1010. So you're able to see 1010, which is displayed as 10 here. A small flickering is happening here, right? So when it displays as 64 means what? So if it is less than 10 means it is easy for us to understand. Now it is 0, so all the LEDs are 0. I am slowly rotating in clockwise direction. The value shows something like 3. So it is something like 11011 So the analog to digital converted binary value shown in the LED. After necessary code converts, like binary to BCD and BCD to 7 segment, it goes to the multiplexer 7 segment display. So with respect to the on-chip peripheral of LPC2148, we can able to see the GPIO parallel port is also working because LEDs are reflecting the analog to digital converter value. So one parallel port which is GPIO and one serial port which is this UART. So through UART, so through this RS-232 serial data transfer, it is going into the PC through UART to USB protocol converter CP210. It reaches the PC and the value is increasing from 0 to 2046 millivolt and 2046 millivolt to 0. So on-chip UART of LPC2148 is being used because of on-chip I2C we are able to display something in the, we are able to see some displays in the 7 segment display. So I2C is working, on chip UART is working, on chip ADC is working, on chip PWM is working, on chip GPIO is working with respect to LPC2148. With respect to VA microsystem kit, onboard peripherals, LED is working, potentiometer is given as an input, analog input, on chip ADC, and 6-7 segment displays as onboard peripheral, and one small LED which is interfaced with the PWM output, and the serial communication port. So several on-chip peripherals and several onboard peripherals helps us to make a proof of concept of an e-bike where the input is analog, the output is also analog. You see, the input is also analog, output is also analog through PWM, and the values are, ADC values are displayed in the 7 segment display using I2C protocol, and the same analog to digital converter values are getting displayed in the LEDs, and it is transmitted through UART to PC to display the converted value. So several on-chip peripherals, we have an exposure to several on-chip peripherals, we have an exposure to several onboard peripherals here, and the coding is the integration of everything whatever we did so far. The coding is integration of everything whatever we did so far. Quickly to refresh the coding means, let me try my best to quickly refresh the coding. This is the coding here, as we see here this coding, all in one, it's given as all in one, where 8 GPIO, 8 LEDs are being used, GPIO in LPC2148, 8 LEDs in VA microsystem kit, PWM in LPC2148, LED brightness control in the kit, ADC part value as PWM duty cycle for proof of concept of e-bike, and the UART and I2C to display the ADC value in a 4-7 segment display. So quickly to refresh, so the multiplex, that 7 segment display code is given as an one-dimensional array as unsigned character, and there are variables to convert binary to BCD code conversion like ones, tens, hundreds, thousands, and there is a temporary variable, integer variable, the long integer variable CDEF. So first you are initializing the ADC by using the pencil register and ADC control registers and the direction register. Then we are initializing the PWM control register, match control register. 0 is a period register, and here latch enable register is being used to vary the PWM duty cycle on the go. And as we know, the I2C initialization is being done, and the UART initialization is being done. So several on-chip peripherals are initialized. As you see, ADC is initialized, PWM is initialized, I2C is initialized, UART is initialized. Getting the ADC value, 10-bit ADC value, and putting in the variable D, and putting that analog to digital converted value as a duty cycle value. You see, D is a variable which is having analog to digital converted value in 10-bit. That is why it is ANDed with 0x3. That 10-bit analog to digital converted value is given as an input to the PWM register, match register 2, which is a duty cycle value for the PWM. So minimum the analog input, minimum the D value, minimum the duty cycle, minimum the brightness, maximum the analog input, maximum the D value, maximum the duty cycle, maximum the brightness. That's what. So that value is, D value is taken to C, and then you are multiplying with 2 and in another variable F, and code conversion happens here, ones, tens, hundreds, thousands. So binary to BCD is happening here, and as we see through I2C protocol, we are sending out. So this is one set to send out, select one segment and sending out the data to that particular segment, right? 7A is the address of the least significant 7 segment display, as you see here. This is 7A address. So 7A selected, and once tens, hundreds, thousand, no? A of ones is given to 7A, and you see tens means 78 tens value, the same code, right? Similarly, hundreds value 76 is the I2C address, selecting the third 7 segment and sending out the hundreds value, selecting the fourth segment through I2C addresses 74 and sending out the thousands value, and selecting the fifth segment, which is not necessary, That's why we are giving the 0, 0 value. Similarly, selecting the 6th segment, that is why we are giving 6th segment by address 70. By giving 0, 0, it will not blow. You see here, the 5th segment and 6th segment is not blowing. Why? Because we have given the value of 0, 0. Only the 4 segments are displaying ones, tens, hundreds, thousands. That is how you have seen here. I-square initialization is happening like this here. Okay. So you see, ones, this is A of ones, is getting transmitted by selecting the least significant 7 segment display. Then by selecting the next least significant 7 segment display, tens are getting transmitted. The next least significant 7 segment display I2C logic is 76 is the address, then hundreds are sent out, and 74 is the address for thousands. 74 is the I2C address for selecting the thousands, so 1000 the data is sent out, and 72 we are sending 0 to switch off the 7 segment, 70 we are sending 0 to switch off the 7 segment, because we know very well the address for those 7 segments are something like this. 70 is an address, I2C address for this 7 segment, and 72 is the I2C address for this 7 segment, 74 is the I2C address for this segment, 76, 78 and 78. So 70 and 72 are made 0 just because they are not necessary for doing things. Okay. Then you can see in this code, ADC variable is sending out through IO1 pin. You can see the ADC value is coming out through the IO1 pin after 24 left shift. After 24 left shifts, that is what getting displayed in the LEDs here. So LEDs are in the most significant bits of port 1. That is why it is left shifted 24 times. The C variable, the output of the C variable is left shifted 24 times. Again, you are doing the code conversion and the serial data transfer. So UART in LPC2148 has line status register. When the line status register value is not equal to 60 means the transmitter is not empty. When it is 60 means transmitter is empty. You are sending the next data through transmit hold register. So by sending ASCII in single quotes, if we give means the corresponding ASCII value. So V space equal to space, because V space equal to space, that is why the serial window shows V space equal to space. V space equal to space. That's what. Then V space equal to space, thousands, hundreds, tens, ones, millivolts. So thousands are with 30, hundreds are with 30, tens are with 30, ones are with 30 means BCD to ASCII code conversions. By adding 30 to the ones, tens, hundreds, thousands, it will become ASCII equivalent of the numbers. That's why we are adding 30. So one dimensional array will convert binary to BCD. One dimensional array will convert binary to BCD, and BCD to ASCII is through this R-ing with 30. So transmitted through the transmit hold register. This particular code, UART output code, V equal to thousands, hundreds, tens, ones, millivolt, helps us to see this corresponding value in the screen as we see here. V equal to some 0.0000 millivolt as you see here. So when I increase the potentiometer, the voltage increases as you see 2046. This is coming just because of this code which is getting downloaded. That's all. So UART code displays the value in the PC as you see here. Similarly, this code conversion, this IO1 pin code C is left shift of 24 is helping us to see the corresponding value in the corresponding LEDs. So maximum all LEDs are glowing 1023. Minimum none of the LEDs are glowing 0. So that is this code, ADC values to LEDs. So then I2C 6 segments. So 6 modules with address 70, 0. Why 0? Nothing to be displayed in here. 70. This is 70, 72, 74, 76, 78, 7A. So 70 should display nothing. 72 should, 7 segment display should display nothing. So this is thousands, hundreds, tens and ones. So 70 nothing, 72 nothing, 74 address thousands, 76 address hundreds, 78 address tens, 7A address ones. So you can see that is how the code has been written. 70, 72 are 00 and 74 thousands. 74 I square C address displaying the thousands value. 73 I square C address, 76 I square C address displaying the hundreds, and 78 I square C 7 segment displays tens, and 7A displays ones, as we know very well. So this is I square C, and again corresponding code conversions are happening. This is the PWM duty cycle values are loaded, which is the output of the ADC, as we see here. That's all. So UART initialization is done here, I square C initialization is done here, PWM initialization is done here, ADC initialization is here. All are put together, which becomes a complete application, which is fantastic. So like this, we can simulate n number of applications by using LPC2148 ARM7 based microcontroller through this VA Microsystem Development Kit, as we see here. Thank you very much.